So next we are going to discuss about the periodic trend of electron affinity. So this one is also a upright property. That means the electron affinity increases in the upside from bottom to top in the group and from left to right along the period. So first let's try to understand what is the meaning of electron affinity. For that we will take example of this. So let's suppose this guy. So this guy likes this woman. Now he is thinking of proposing this woman. So he went with a bouquet of flower and he proposed. Now it's up to this woman that whether she will accept this flower or not. If the women like him back, then she will accept it. She will say yes. But if she doesn't like him, then she will say no. So it's actually the decision of the women, right? Similar thing happens in the atomic world, that when you are trying to put an extra electron to an atom, so that time the atom, the atom is accepting that maybe that atom is accepting that electron, or it may be reluctant to take that electron, right? That's why let's take the definition. Let's see the definition now. So electron affinity is the amount of energy released when an electron is added to the valence shell of the isolated gaseous species. It may be atom, ion or molecule. So you are trying to add an extra electron in the valence shell of the isolated gaseous species. Now if the atom is willing to take that electron, then the energy will be released, and if the atom is reluctant to take that electron, then you have to give some energy, you have to put some energy. So this one was the older definition, and recently it has been changed, and it is said that energy required to detach an electron from the singly charged negative ion. So the energy for the process of x plus E is equal to x minus. So the same thing, as you are adding an electron to the atom, or you are detaching an electron from the singly charged negative ion. So already you have added the electron to the atom, now you are detaching that extra electron. So it is just two different ways to look at the same incident. Is it clear? So you are trying to put an extra electron in the atom. Now depending upon the atom's electronic configuration, it might take the electron, and then if it easily takes, it will release the energy, and if it doesn't want to take the electron, then you have to provide extra energy. Now let's take some examples. So some atoms readily attract electrons, and the electron affinity has a negative value, meaning that energy is released, as I was talking. So in this case the girl said yes to that person because the girls like him back. So that's why you can see, if we put an extra electron to the chlorine, the delta H of this process is negative. So it is exothermic, minus 349 kilojoule per mole. So the chlorine atom easily takes electron. Most atoms, however, do not accept additional electron readily, and the electron affinity is a positive value, indicating that energy must be used to add the electrons. For example, nitrogen. So we have already seen that nitrogen has half-filled configuration. So if you want to put one electron, it is not energetically favorable. So the nitrogen atom will not try to take this electron. So if you have to force it, you have to put extra energy to make it N minus. So that's why the enthalpy of the process is positive, plus 20.3 kilojoule per mole. Now things to remember, that positive value of electron affinity indicates endothermic process, which is not favorable. That means you have to invest energy, you have to put more energy. And negative value of electron affinity indicates exothermic process, which is favorable, readily acceptable. Means chlorine is readily taking the electron. Similarly, fluorine is readily taking the electron. So if the electron affinity is negative, the process is favorable. Now let's see the periodic trend of this electron affinity. So as we go from left to right along the period, the electron affinity increases. And as we go from top to bottom along a group, the electron affinity decreases. So what we can say, along group, if we go bottom to up, the electron affinity increases. So it is increasing from left to right and bottom to up. So actually it is increasing in this diagonal way. That's why I call it upright property or UR property. Now let's see the 3D plot, 3D bar plot for this electron affinity values. You can see as we come from left to right, the electron affinity increases. And as we go from top to down, the electron affinity decreases, right? So what are the reasons behind it? So we will try to understand. For this, I will take this pen. So principal quantum number is fixed along period when we go lithium, beryllium, boron, carbon. So that time the principal quantum number is fixed or the number of orbit is fixed. Shell number is fixed. Effective nuclear charge increases. So we have already seen that as we go from left to right, the effective nuclear charge increases and size gradually decreases. So same thing we have already seen during the atomic radius, periodic trend of atomic radius, atomic volume, all these things. So as we go from left to right, so we put more and more protons, means the girl is more and more attractive. So that's why these boys, these electrons which are in the outermost shell, they feel more and more attraction towards this girl. So that's why they shrink, right? The size is also decreasing and the effective nuclear charge is also increasing because we have more number of protons in the nucleus. Now when we put more and more electrons, when we go from left to right, so electron repulsion also increases, but you can ignore this fact. That's why I have marked it in red. This contribution is very minor and the other contribution uh, that decides what will be the effect. Okay, so this point is just for your understanding and learning. You can ignore this point for considering the electron affinity trend. So thus the electrostatic attraction of nucleus towards incoming electron increases along the period and electron affinity increases. That means when we are trying to put another electron from here to this valence shell, so as we are going left to right along a period, we can see this electrostatic interaction of nucleus to this valence shell's electrons are increasing. So if we put one more electron, it will easily come and the nucleus will attract it with more electrostatic interaction, right? So that's why it will be a favorable process. So as we increase the number of protons, the electrostatic attraction increases and electron affinity also increases. If we place another additional electron, that will easily come and sit in the valence shell. So that's why along a period, the electron affinity increases. You can see here from the graph, here you can see lithium, beryllium, boron, carbon. Those things we will discuss. Now let's see along the group. What is the trend along group? So along group, what are the factors are there? Size of the atom increases. So as we go from top to bottom, we have more and more shells or orbits. So that's why the size of the atom increases. Now effective nuclear charge slightly increases, which acts in the opposite direction. But this point is minor, so we can neglect this point. So this is written in the red. This is a minor factor. Now incoming electrons are placed in a higher energy level far from the nucleus. Let's try to understand what it is written here. So when we have let's suppose an element which has only two shells, and when we go from top to bottom, let's suppose we have another atom which has, so I am drawing it half circle. This will be actually full circle. Okay, my full circles are not good, that's why I'm just drawing half circle. Oh, my half circles are also not good. Anyway, so try to understand, when we have this element which has only two shells, as we go along the group and we have another next atom which has three shells, next atom which has four shells. So when we are trying to place an external electron, we are actually placing the electron here in the second shell, right? But in case of this, when we are trying to place an additional electron, we are placing the electron in the fourth shell. So this nucleus is much more closer in this case. The nucleus to the incoming electron distance is lesser in this case, whereas in the right hand side, the nucleus to this distance is much more. So as the distance increases, the electrostatic attraction decreases. So here the distance is less, so the attraction is more. So you can in terms of girl, you can figure out that if the boy is close to the girl, if they meet regularly or they are very nearby, they live nearby, then there is a high chance that there will be more attraction. But if the girl is very far away and the boy is in another city, so in that case it will be difficult, the attraction will be less, right? They will meet very less, it will not be frequent. So the incoming electrons are placed in a higher energy level far from the nucleus in case of these elements where we have more and more shells. Thus, the electrostatic attraction of the nucleus towards incoming electron decreases along the group, and electron affinity also decreases. So as we go from top to down to the group, the electron affinity decreases. You can see from here, fluorine is here, then bromine is less, iodine is much more less. So electron affinity decreases along the group. But there are some exceptions. So 3p elements, they actually have higher electron affinity compared to 2p elements. But according to the periodic law or periodic trend, actually it should be the opposite. You see here, the electron affinity is actually decreasing, right? From top to bottom of the group. So this fluorine, when we are going fluorine to chlorine, the chlorine's electronegativity should be lesser according to this periodic trend. But actually, this chlorine's electronegativity is more than fluorine. Or in the other language, we can say 3p elements have higher electron affinity compared to 2p elements. Now let's see the pairs. So we have fluorine and chlorine, and this is the electron affinity value. So chlorine has higher electron affinity, and in the pair of oxygen and sulfur, sulfur has higher electron affinity. In the pair of nitrogen and phosphorus, phosphorus has higher electron affinity, and in the pair of boron and aluminium, aluminium has higher electron affinity. But the electronegativity trend is actually completely opposite. Now why so? What is the reason behind it? So to understand that, we have to consider these 3 points. So first one is 2p atoms have smaller size and greater electrostatic attraction. So the 2p atoms, they have smaller size. So smaller size means greater electrostatic attraction towards the incoming electron. But the extra added electron creates electron-electron repulsion. So although it has higher electrostatic attraction, that's why the electronegativity is more in case of 2p elements. But the extra added electron, if we add one extra electron, that creates electron-electron repulsion in that valence shell. Now the repulsion is large in second period elements, but the repulsive force is not so large in the third period element. Now in the third period element, in the 3p has bigger size compared to 2p, right? So when we are adding electron in the 2p, that time electron-electron repulsion is very high. But if we are adding electron in the 3p, that time it can manage, it is not that much high. The next point is possibility of delocalization of increased electron density in vacant 3d orbital reduces the repulsion for third period elements. Now in case of third period elements, they have a vacant 3d orbital. So the incoming electron, which is increasing the electron density, so the atom can pass that electron density to the vacant 3d orbital. And in that way, it can reduce the electron-electron repulsion, right? So that's why these 3p elements, they have higher electron affinity, whereas 2p elements, they have higher electron negativity. What is electron negativity? We are going to learn after this electron affinity. Okay, so just remember these 3p elements, they have higher electron affinity because the electron-electron repulsion is less, because the electron can be delocalized in the vacant 3d orbital. And these 2p elements, they have lower electron affinity compared to the 3p because of the increased electron-electron repulsion. Okay, now we will see in case of d block elements. So sometimes electron affinity do not show apparent trend. For example, electron affinity of manganese, which is half filled, and zinc, which is full filled, is 0. So this is the electron affinity data for d block elements. Now if you see, so we said along the period, if we go from left to right, the electron affinity increases, right? So from here to here, the electron affinity actually should increase. And we can see in the case of titanium, vanadium and chromium, the electron affinity is indeed increasing. But in case of this manganese, the electron affinity comes to 0. And from here to here, again the electron affinity is increasing. But again in case of zinc, the electron affinity is 0. Now this happens because in case of manganese, I will show you the 3D cell. So in case of manganese, the 3D is actually half filled. So in case of manganese, it is 3d5. One electron here, another electron here, another electron here, here, and here. So I have already taught you that when it is in half filled situation, that time the exchange energy is very high. Exchange energy contributes in the stability of the system or stability of the atom, right? So in case of manganese, it is 3d5 configuration, electronic configuration. So these 5 electrons are having much high exchange energy. So that's why it is very stable structure. And this manganese element or atom, they don't want additional electron. If the additional electron comes, it will come and sit here and it will do the pairing. So this manganese do not want that. That's why this half filled configuration is having 0 electron affinity. Similarly, in the case of zinc, zinc is actually 3d10. So there are 5 more electrons here, 7, 8, 9, and 10. Here also you see we have these 5 electrons of same spin, and we have these 5 electrons of same spin having down spin. So now these 5 electrons can be stabilized due to the exchange energy. Okay, due to exchange of their position, they can give extra stability to this atom. So that's why zinc also do not want to get additional electron. So that's why the electron affinity is 0. Now the next factor is because of lanthanide contraction, the post lanthanides show unusually high electron affinities. Now lanthanide contraction I have already explained in the lecture 5. So as these F electrons have less shielding effect, so the atom size actually contracts, it shrinks. So because of that, the atom size is very small and the nucleus to valential distance, the radius r or atomic radius, that is very less. So that's why the nucleus is having higher electrostatic interaction to the incoming electrons, right? I will simply draw it for you. So this is the nucleus and there are multiple shells. Now consider this, that there are F electrons here in this layer. Okay, just consider F electrons are here. Now F electron has very less shielding power. So what, and it is diffuse in nature, less shielding power. So what happens, the next orbit, which is after this F, whatever will be the next orbit, so that electrons, they experience high attraction force towards this nucleus. So this orbit actually shrinks, it comes closer and it comes here. So as it is shrinking, you can see the distance is decreasing between the nucleus and this valence shell where is the electron density is maximum. So this distance, which is denoted as r, this distance is decreasing now. So this nucleus can now have higher electrostatic interaction. So if you want to place another additional electron, if this F electrons were not there, you had to place it here. But now as you have F electrons, D electrons, because their shielding effect is less, this orbit has shrinked here. Now you are placing this electron actually here. So much closer to the nucleus. So that's why they have unusually high electron affinities. These post lanthanides have unusually high electron affinities. For example, gold has a very high electron affinity, which is 223 kilojoule per mole. So among the metals, gold has the highest electron affinity. Now for your reference, you can check this data. Here I have mentioned the electron affinities. You can see the electron affinity values here. Now you can see greater than 0 means it doesn't want to take electron. These are having a full-filled shell. That's why the electron affinity is greater than 0. They don't want to take electrons. Similarly, nitrogen also greater than 0. And especially these inert gases also. They have also full-filled shell. They also don't want to take electrons. And the electron affinity is greater than 0. Whereas if you see this fluorine, chlorine, bromine, iodine, they have negative, very high negative electron affinity. So they readily accepts that electron, the incoming electron. So let's see some key points, whatever we have learned in this lecture regarding periodic trend of electron affinity. So we found out that this is a upright property. So it increases in the from left to right. If you go along period, it will increase, and if you go bottom to up along a group, it will increase. Do not get confused with the term electron affinity with electronegativity. So electron affinity is a discrete atom's property. So electron affinity is actually an inherent property of the element or the atom, whereas electronegativity is the property of a molecule, so bound with another atom. So one atom will have single electron affinity value, but it can have multiple electronegativity value depending on its environment, depending on its with which atom it is bound. Okay. Metals like to lose valence electrons to form cations to have a fully stable octet. They mostly don't like to take electrons. So that's why for metals, the electron affinity value is very less or maybe sometimes greater than 0. For alkali metals, NS1 electronic configuration, the accommodation occurs in NS level and gives NS2 configuration. Whereas for alkaline earth metals, they already have stable full-filled electronic configuration. Thus, the process is favored more in group 1 compared to group 2. Because that group 2 elements, they have already NS2 configuration, full-filled configuration. So they are not favorable, they do not favor, they don't want to take the additional electrons. Whereas the group 1 elements having NS1, they can take the electron and they can achieve NS2 state. Nonmetals like to gain electrons to form anions to have a fully stable octet. They release energy, that means it's an exothermic process, to gain electrons to form an anion. Thus, electron affinity of nonmetals is mostly negative. That we have already seen in case of fluorine, chlorine, bromine, right? Those are having negative electron affinity values. Elements with electronic configurations of NS2, full-filled diamagnetic atom with no unpaired electron, NS2NP3, that is half-filled, and NS2NP6, those are the inert gases, have positive electron affinities because they are unusually stable. They are very much stable, these full-filled and half-filled configurations. So that's why they have positive electron affinities value. They don't want to take additional electrons. Okay.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.